Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In our previous lecture, we had been talking about a special type of transition metal sigma alkyl complexes, and these are called transition metal perfluoroalkyl complexes, and they are represented by Tm, R, F type complexes. And these transition metal sigma perfluoroalkyl type complexes are very stable as opposed to transition metal sigma alkyl complexes, which we have also discussed prior to discussing these transition metal perfluoro sigma alkyl complexes. These are alkyl and these are perfluoroalkyl. One of the attributes of transition metal perfluoroalkyl complexes is that they are more stable due to high or probably the highest bond energy, more stable. Also, we had seen that these compounds show unique reactivity which are absent in their transition metal sigma alkyl counterpart, that arises due to reversal of polarity and lastly, we had seen that of all the type of activations, bond activations, for example, in this case see H bond activation or C bond activation. In case of transition metal perfluoroalkyl, CF bond activation was most challenging, and we had also seen in our previous lecture some of the examples pertaining to CF bond activation, not only in a stoichiometric fashion, but also in catalytic fashion using a rhodium catalyst. In today's lecture, we are going to look into something along this line, and these are transition metal sigma alkenyl, aryl or alkenyl type complexes. So, these are transition metal complexes with CsP2 type hybridization, and for this one it is CsP type hybridization, whereas for the ones that we had studied so far, these had CsP3 type of hybridization. So, these ligand CsP2 and Csp type, this alkenyl or alkenyl ligands, they occupy a position between sigma alkyls, that is Csp3 type, and sigma donor pi acceptor ligands like carbon monoxide, PR3, RNC, etc. So, today's lecture will focus along this line, looking into various types of transition metal sigma alkenyl, aryl and alkenyl complexes. Now, in terms of transition metal sigma alkenyl complexes, they can bind in both bridging and terminal fashion, as can be seen here. This is a terminal binding, or it can be a bridging type of something of this which can be bridging. So, this is transition metal alkenyl type of moiety. Transition metal aryl can also display similar terminal as well as bridging binding. The terminal is shown over here and the bridging can be of this type, and lastly, so this is CsP2, this one also is a CsP2 type, and lastly for transition metal alkenyl, which is CsP, it can be as well terminal as well as bridging. The way as shown over here. So, these three types of compounds that show different additional bridging modes as opposed to simple the terminal ones would be the ones that we are going to be discussing in this next series of lectures, and they are primarily focused on transition metal CsP2 or transition metal CsP type of functionality. Now, one interesting thing that one moves from, as one moves from transition metal CsP3 to transition metal CsP2 to transition metal CsP, the covalent radius of carbon changes, and with the increase in S character its covalent radii decreases. For example, for sp3 it is 77 picometer, whereas in sp2 as the S character increased, because of that the radius of carbon has shrunk to 74 picometer. To CsP it has come down to 69, where now there is more S character picometer. So, as a result, this transition metal, if these three hybridized carbon binds to the same transition metal, then their bond length is supposed to shrink. If the transition metal remains the same, and if it binds to 3 different hybridized carbon, the overall transition metal carbon distance is supposed to decrease as the covalent radii of carbon would decrease from sp3 to sp2 sp, whereas the covalent radii of the transition metal would remain the same. And this can be seen in this particular example, where this platinum is bound to PPH Me2 P pH Me2 chlorine and CH2 Si Me3. So, this has a sp3 carbon and it has a platinum 2 center. Platinum 2 covalent radii is 131 picometer, and in this case the platinum carbon bond distance thus would be 208 picometer. And what is the observed as well as the calculated one, which can be done by adding the covalent radii of sp3 carbon and platinum, they match up very nicely. Now, in another related complex, similarly, when platinum is bound to 2 phosphorus pH Me2 P Me2 pH chloride and CH double bond CH2, where the carbon is now CsP2 center. The platinum radii, this being platinum 2, would remain the same as 131 picometer. So, that would predict this platinum carbon bond to be 131 plus 74 picometer, and the observed bond distance is almost close and found to be very close to be 203 picometer. Now, when one goes to the third sp type of example, where this analog, where platinum is bound to pH Me2 P Me2 pH chlorine, and now there is a sp center bound to platinum. So, hybridization over here is CsP platinum in +2. So, its covalent ionic radius would remain the same, and that would predict this to be 200 picometer, but the distance is even smaller and found to be 198 picometer. So, only marginal difference exists between the PTC bond length, only a marginal difference exists between calculated and observed platinum carbon bond length. This shows that how the change in hybridization would result in variation in the bond, and that would end up being bond being getting shortened with the increase in S character. We are going to now discuss some of the methods available for preparation of this transition metal alkenyl complexes. The foremost method is oxidative addition of HX of HX to an activated eta 2 alkyne complex This is best represented by R3P whole to PT having an alkene bound to it results in reacting with HCl moiety and HCl protonating the alkene and platinum getting chlorinated, giving the R3P whole 2 chloride PT R H R as a result of oxygen addition, whereas to begin with in this eta 2 alkyne complex the platinum 0 which resulted in oxidative addition. It must be noted that 0 valent platinum or electron rich platinum was crucial to having this alkyne adduct, where the alkyne adduct was stabilized by electron donation from platinum onto the alkyne portion. Another method in synthesis of alkenyl complexes also involve reaction of similar eta 2 alkyne complex with a nucleophile. The first one was eta 2 alkyne complex undergoing oxidative addition. In this method, this is a slight variation as to having a nucleophilic addition to a cationic alkyne eta 2 complex. The second method thus involves nucleophilic addition to cationic eta 2 alkyne complex. So, for example, this iron alkyne complex which is cationic in nature reacted with Li2 Cu Cn pH 2, where pH minus is the nucleophile that attacks at the olefin, giving this alkenyl complex of iron as shown here. So, what we see is this nucleophilic attack on this alkyne resulting in a phenyl over here. So, it must be noted that nucleophilic attack to an alkyne is counterintuitive, because nucleophile as well as alkyne both are electron rich. However, when alkene or alkyne gets coordinated to the metal center in the coordinated state, it becomes amenable to nucleophilic attack, and such is called the Umpolong nature or reversal of polarity. of alkyne or alkene, or it is called Umполong reaction. So, here is another example whereby this Umполong nature of alkene and alkyne upon coordination to iron has been utilized in synthesizing this iron alkenyl complex. Another example involves this vinyl group acting as a bridging sigma pi bridging type of ligand, and this is obtained by CBr addition to iron carbonyl compound. So, this method involves low valent iron dicarbonyl reacting with one 2-dibromo ethane, where the CBr insertion happens, resulting in the following iron compound. And alkenyl compound. So, one note that this bromide and this carbon, there is a activation that has happened over here, resulting in this kind of sigma pi bridging ligand, sigma type of bridging mode. This is an interesting binding mode where this is the sigma and this is the pi type binding that this compound is displaying. Now, one interesting thing as opposed to with regard to this metal alkenyl complex is that most of the preparation has been achieved by the reaction of coordinated alkyne onto a metal center, followed by oxidative addition or by nucleophilic attack. From this perspective, this particular method of synthesizing iron or metal alkenyl complexes, where there is a CBr activation occurring on a low valent iron complex, becomes useful. So, with this, let me summarize what has been discussed in this lecture, which were on metal sp2 type interaction. In the beginning of this lecture, we have covered various kinds of ligand displaying metal sp2 as well as sp3 type of interactions. For sp2, this includes metal alkenyl, metal aryl, and for sp type of interaction, this included metal alkynyl type of complexes. We have also looked at the binding mode of this metal alkenyl, aryl as well as alkynyl type of complexes. We have looked into various synthetic methods which are available for metal alkenyl complexes, which primarily involved the reaction of eta 2 coordinated alkyne onto a metal center, followed by oxidative addition or nucleophilic attack, as well as by CBr activation of a alkene onto a metal low valent metal carbonyl compound. It must be noted that the second method which that involved nucleophilic attack on a metal coordinated alkenyl system involved the Umполong reactivity or the reversal of polarity that arises because of alkyne coordination to the metal. So, with this we looked into various synthetic methods available for preparation of metal alkenyl complexes, and we conclude today's lecture, and in next lecture we are going to look into more details at metal aryl as well as metal alkenyl type of complexes. I thank you for being with me in this lecture and look forward to being with you in the next lecture. Till then, goodbye and see you in the next lecture. Thank you.